Okay, hello everyone. My name is Eli Barkai. I'm going to give this course on stochastic processes in physics. I hope you enjoy it. Basically, what I will try to do is give you a review of the old theory. Old, I mean, let's say, roughly from beginning of the 20th century and backwards, but also the more modern theory. So one example will be already today. So today we will focus a little bit more on mathematics, I would say. I will present to you something that most of you might know, and that is the Gaussian central limit theorem. But I'll also present, which is a really old stuff, 200 years ago. It was not invented by Gauss, by the way. Who invented it? You don't know. A guy called de Moivre. He was sitting in the pubs of London and he was throwing dice, and people used to come to him and they were asking him to evaluate the chances of them winning in bets. You know, you want money, right? Everyone wants money. So he was calculating, let's say you have a random walker. What is the random walk here? You have money, but sometimes you get one coin more or one coin less by probability half. That is like a random walk. This is the money axis, and then I get, by chance, with probability half, I get one more coin. I'm here. But maybe I lose, so I go back. And then I win a few more times, like this. Then I go like that. So this is money. This is very important. And money drove the central limit theorem. For this random walk, he asked how much money will you have after a long time, after many times you toss this coin. And he found, using the Stirling approximation, he found something like a Gaussian. And today we call it the normal distribution. Why is it normal? Because it's found in many applications, not only in physics and chemistry, but even people in sociology. They fit everything to this bell curve, which is a famous normal distribution. Of course, it's called Gauss because of a good reason, because de Moivre, he looked at very particular random walk. You jump with probability half to left and right. Gauss was a really great mathematician. He proved it in a more general way, not for something specific, not for a specific case. So de Moivre's random walk, which you jump left and right, is called the binomial random walk, because the probability, you can show it's related to the binom. We will show this later. And this is only example of one random walk. Now, when I say random walk, I showed you it comes from money, but it can come also from a particle in a medium. So if you put a particle in a medium, so this is liquid, let's say this is water at room temperature, and here I put 1 micron, some small bead, and I follow it, then what you will see is a kind of random walk motion. This was already shown in 1827, more or less, by Brown. And what he saw in the microscope, he took some particles. It's very strange, but he took them from the Sphinx in Egypt. He took, there was some British expedition that went to the Sphinx, and they brought to England some part of the Sphinx. And he used this stone, and he thought maybe you can find some animals inside. So he put it in water, and he said, okay, if these are animals, they can move. So, and then he saw, wow, at the beginning he saw these guys are moving. So he thought, wow, I found something interesting in the Sphinx. There are some old animals or something that are living when you put them in water. But then he put all kinds of other things, like he took some coal, he took some sand, he took many things. He was very good experimentalist, and he saw that all of them, when you put this micrometer, all of them doing the same. Then he was very disappointed, because it's not life moving there, it's some physical phenomena. For him it was a great, I guess it was very bad news, But actually he became famous because of this, because what people understood later is that when you put in room temperature, you put something small enough, it will do this motion, which is a kind of random walk. You jump sometimes to the left, you jump sometimes to the right. But today we call this type of process, we also call Brownian motion, after this botanist. So you see already here, you see that these stochastic processes, they come also from finance, they come also from physics, they come also from botany and many, many other fields. And generally speaking, just philosophically maybe, in physics we have deterministic motion. So we have Newton's set of laws, which are totally deterministic. And of course, when you deal with macroscopical bodies like the moon rotating around the sun, to the first approximation, this is deterministic motion. It's determined by the initial condition, the velocity, and the force field. It's absolutely true, of course. But what is in real life, there is always two things that are missing in this description by Newton. And these things are very important. And one of them is friction, that you are usually in a medium, and that means that you lose energy, you exchange energy with an environment. And the other thing is fluctuations. And this is an example of the fluctuation. This erratic path that you have here is a random walk path. So these type of motions exist everywhere. For example, if you look in you have a cell in biology, and you put some messenger RNA in the cell. You look at it under the microscope. Today you can do it with importantly one molecule at a time, and you will see it's doing some random motion. So randomness is everywhere. You can think about this. If you have an electron in a condensed matter environment, then if you think that it's going ballistically, moving straight, it's of course wrong, because it's always colliding with many things. If you take the stars, they also move, but then they collide with another star, and then their motion is, it depends on time scales, of course. So for some time scales, you can see more or less deterministic motion, but after some times, also in your life, you will meet someone, you will collide, and that will change your life, and you will become random. That's the way it goes, and that's the reality of life. The beauty of Newtonian mechanics is that he was able to understand that while all life is random and all life is with friction, it's better to think about things at the first without them. So the first thing physicists do is let's get rid of the noise, let's get rid of the friction. But in reality, it's the opposite. We want it exists. That's the fact. So now this course is more or less motivated by this. And this was, for example, in this experiment by Brown, but the physicists came in a bit later, 1905 to 1908, very quickly. There were 3 people, or maybe more. Langevin, Perrin did experiments. He got a Nobel Prize on this issue. Why did he get a Nobel Prize just on something Brown looked in the lab? Well, maybe we should talk about this. What Einstein understood, so another guy was Einstein, I think you heard about him, Smoluchowski and others. Also Planck, the famous Planck from quantum mechanics. Why is this guy actually moving in an erratic way? What is happening here? Why, when you put a small molecule in water, for example, why is it moving like, we call it a drunk random walk? It's moving like a drunk guy, jumping left, right, all the way. So what Einstein understood is the following. This guy is in water, so it collides with water molecules. It's all around here. And then these water molecules are bombarding it, giving some momentum in this direction. But of course, the other guys are giving in the other direction. Also, when you are sitting here right now, you have some air coming and hitting you from this side and that side. But because you are very big, you are more than 1 kilogram, it doesn't really matter. because it's kind of balanced. You're getting all the time small little hits, but they are balanced. But if you would be small, the fact that sometimes you get a little bit more hits from one side and less hits from the other sides will give you a random motion. And this is what Einstein understood. And then he said, wait, but then this is related to the microscopical theory of the surrounding. The fact that the surrounding is built out of atoms, not out of a continuum. So if you think about this water, let's say with fluid mechanics, the water is described by some field equations. You have a density, you have maybe a velocity field, but you know, there's a flow here. But really what is driving things is that some small atoms, discrete atoms are here, and they're hitting on one side more than the other, causing fluctuation to here, causing fluctuation to there, etc., etc. So Einstein built a theory that shows how this phenomena of Brown is related to the fact that we have atoms. Now at the time, this was a big issue because people didn't know that atoms exist. Now we know that it exists. So the way atoms were discovered in some sense were based on this type of motion. Perrin was able to use these experiments and a theory developed by Einstein that I'm not going now into details, will come later in the course, to measure the Avogadro number. The Avogadro number was an indication that really we have atoms around here. This number is important in this type of experiment. And that's why Perrin got a Nobel Prize. It's strange, Einstein didn't get a Nobel Prize, but he got a Nobel Prize on other things, so it's okay, I guess. So this is related to really many things. Another example is, for example, in chemistry, let's say you have now two of these Brownian particles, or maybe one particle maybe we fix in space. Let's say this guy is a heavier guy, it's not moving, or we take a hammer and we put it here. And we call it, this guy, let's call A, and this guy we call B. So what is happening is this guy is moving in a random way. And it can happen that this, let's say this is a molecule, it can happen that this molecule is moving and then it's arriving here. How is it arriving? There is a very complicated path. This is the random walk path, which we need to understand in the first part of the course. But then, if we are lucky, the particle goes, and back it reaches here. What is this thing? This is a chemical reaction. This is a chemical reaction which is driven by diffusion. So the process is random, and then how long does it take the particle to go from, let's say, here to here? It depends on the path. If by chance, for example, this guy happened to go this way at the beginning, it will take him a long time to reach here. If by chance it went like that, it might take him a shorter path. So you have a distribution of times of arrival of molecule B to molecule A controlling the chemical reaction. And this chemical reaction is what is driving all your cells, etc. You have two molecules, they need to meet, and they need to change some chemical information. So everything is done in a stochastic way. And for that you need to know, first of all, you need to know what is the statistics of the path, how do we describe it, etc., etc., in order to know how long it will take him to create these things. So everything in a lot of chemistry is described by these first passage time problems, and of course this doesn't have to be a first passage time of molecule A to molecule B. You can think about many problems like this. For example, let's say you have electricity and you have some Ohm's law, so you have some voltage falling on some resistance, and then you have some average current. So what you were taught in high school is average current. It's always average. In reality, you always have some fluctuations. These fluctuations are because, let's say, the conductor is heated or something like that, or whatever. It's not, we're not saying why. Now, you might be interested in the question, when is the first time this guy arrives some threshold? Why is it important? Because if, let's say, your conductor breaks, when it arrives at this current, this is when the system will fail. This is what is really important, because if this threshold is very low, it will break very quickly. If this threshold is high, it will break after some time. If you are in a company, what do you want to do? You want to make this high or low? High. You're wrong. They want to make it not high and not low, because they want it to break, and then you can buy another one. I'm not kidding. They design it in such a way. Okay, you can put it more seriously. You want to put it high in such a way that this will live long enough for you. Of course, in real life, it will depend how difficult it is to make this threshold high. This depends on the material. It's a very complicated problem. And what are your goals? You want to make it high, but not too high. If it's very low, of course, no one will buy your machine. If it's too high, you buy it one time, and then you will not come back. So you have some optimum, which that's what engineers do. And this can be, of course, also a stock market that is fluctuating, or a stock, and then you want to sell it when it reaches some threshold, and you want to know when. So all these stochastic processes, again, enter in many, many fields. I just want to say here one simple message. This course is useful, but it's not only useful in physics, it's useful in many disciplines of science. So that's the reason why I'm going to be general. It's not going to be only physics course, but it will be oriented towards physics, but many things can be applied in other cases. So now, with respect to the textbooks of this course, there are not really one good textbook. On my webpage, you can find some summary that I wrote maybe 10 years ago on this course, but I always change this course. There are basic I studied with some guy called Martin Bazant. He's a guy from MIT. And he had a nice course, so I took some of it from here. You can find it on the internet. There is also a guy from, but I'm not sure the book is out. This is an Israeli guy, but he's now in Harvard. He also has some nice book out in the market soon. There's a book called First Steps in Random Walk. This is a real book. It's published. It's published by Igor Sokolov and Yossi Klafter. Yossi Klafter is a chemist from Tel Aviv University who was the head of the university, and he did a lot of work on random walks. So many Israelis did a lot of work, including in this university. There is a book by Ben Avraham and Havlin. So Havlin is a well-known figure here. Really did beautiful work on random walks, but then moved to network theory. All these, I would say all these books have elements of the new and the old kind of together, but none of them will really help you. You just need to find one book and read it if you want to read it. There are all the books that deal with the classical theory without the modern theory. And these are books by Risken on the Fokker-Planck equation. A book by, which I like, or I used to like, by Van Kampen. Stochastic Processes in Physics and Chemistry. And there are other books. There's a book by Kubo. Kubo is a very famous Japanese guy in statistical physics. His book is called Statistical Physics 2, I think, or something like that. It's with two other guys, StatMech or StatPhys 2. In some sense, we are doing StatPhys number 2, but only in some sense. What is usual statistical physics? It's in equilibrium. There's no time in it. Things are static most of the time. We are dealing all the time with processes and random processes. So in that sense, we are continuing statistical mechanics 1. I would say that the theory of non-equilibrium, that is time-dependent phenomena of stochastic theory that is in this course, is very, there are many general things, general items here, but the fundamental issues are not so clean like equilibrium statistical physics. So you would see there are many approximations. The theory is much more complicated in some sense, maybe less generally valid. It's not like the canonical ensemble that in equilibrium we can really say a lot, because simply said the phenomena is more complicated. So that's why stochastic processes are so important, because they give you a tool to describe the processes, even though we not always understand the basic microscopics. So many of the theories are phenomenological. You describe something, you don't understand it completely. For example, we assume there is a friction. It's behaving like this. We take this, good, it's true, and then we build a theory. We don't say, why is this friction like this? That's a microscopical theory. In many cases, this is the case, but this is good enough to describe a lot of the experiments. So what we're going to start right now is discuss a little bit mathematics. And I will introduce you to something called characteristic functions. So I assume most of you heard about this. Essentially, these are Fourier transforms of probability density functions, but we're going to use them all the time, so I want to present it now quickly, unless you have some general questions on the course. No. Okay. So let me introduce the basic notations. I want to denote Px x as a probability density function of a random variable capital X. Later on in the course, probability density function, this will be PDF. And random variable will be RV. Of course, you encountered probability density functions. For example, the amplitude of the wave function in Schrödinger equation, absolute value squared, is a probability density function. So it's nothing new. I just use this notation. I use here the random variable and x. So for example, in these examples I will consider now, x can be anything between minus infinity and infinity. So this is some function, and it has two very basic properties. One of them is that this function is non-negative, because the probability cannot be negative. It's of course real. And of course we also introduce the normalization. So if you think about the coordinate x, this, let's say, is a coordinate of a location of a particle in some medium in one dimension. So this object, I think, as you know, means the following. If I multiply it by some small delta x, this is the probability of finding the particle in a small interval x plus delta x. And delta x goes to 0. Now, of course, there is an infinite number of these type of functions. For example, this PDF can be a Gaussian or something like a Gaussian. And this just means, if this is x, there is a higher probability to find the particle or this random variable here if compared to here. So this is the typical fluctuations here in the middle. You have some width of this function. So for example, let's say the distribution of your heights, the average is 1.80 meter, and you have some distribution. Some guys are smaller, some guys are taller, some guys are less tall, and you have this type of well-behaved, for example, PDF. Of course, you can invent as many PDFs as you want. For example, this is called the uniform distribution. The distribution in physics, at least, is the integral over this PDF. But sometimes I switch between distribution and probability density functions. It can be exponential. You can have delta functions if you wish. For example, 2 delta functions. You can have, I'm just plotting here only symmetric ones, so they are symmetric with respect to 0, but they can be non-symmetric, of course, also. And I will plot here one other guy, which has what we call soon fat-tailed PDF. For example, a PDF that decays here like a power law, let's say like x to the minus 2. All these examples are called thin-tailed. This guy is called fat-tailed because the far tail in this positive x decays like a power law. It's very slow. Soon we'll understand what do I mean by slow. Why is this slow? Does this guy look very different than this guy? When you look at them, they don't look different. But when we'll consider the theory of these type of distribution, you'll see this is world number 1, this is world number 2. This belongs, all of these guys, in some sense, are attracted to one distribution. What is this distribution? The Gaussian. These are attracted to the Gaussian, and these guys are not, this guy and many others are not attracted to the Gaussian. What do I mean by attraction? You will soon see. So, before going into details, we of course can calculate moments. So these are moments of the distribution. And I can say that if you have your n equals 0, this is just normalization. Then the zeroth moment is 1. You have the first moment, which in these examples from symmetry are 0. You have the second moment, etc., etc. As you know, many times people use this variance, and they use this sigma to describe the variance. So this is just definitions. I'm just defining things that you will later use during the course. Now, I guess you know this, but still, let us write down a special PDF. One over pi divided by times A. This is something that maybe you're not familiar with. This is a PDF because A, it's positive, and you can easily check that it is normalized. This PDF has a name. Its name is Lawrencium. A here is some parameter. Don't think about A. Say A is 1 if you want. It has a scale. A is the scale. This PDF is decaying like a power law. So this is an example. It's plotted here. This is the Lawrencium. But it has this very special property that its second moment is infinite. So if I measure you guys, it's not true, but for example, if I measure, this was a real experiment, Stas Burov told me. Some guy measured the width of the chest of some Scottish soldiers because he wanted to build uniforms for these soldiers. So you want to know the distribution of the size of the chest. Why do you want to know the distribution? Because then you'll produce, manufacture all kinds of shirts in different sizes, and it will fit this. And this follows more or less the Gaussian. But let's say that you plot, it's a Gaussian around the mean, of course, there's no zero. There's no negative size of chest, so it's a shifted Gaussian. But in principle, you can measure things, and we will see many examples later. For example, the distribution of forces on a star. It's very broad, and it decays like a power law. Or let's say now, this is just a mathematical thing. You can get a distribution whose second moment is infinite, which is not trivial, or maybe it is, but I'm not sure because I think about it so long. I'll explain why it's not trivial. Because most likely you are mixing between probability densities and sampling. So these are two different issues. But first, why is this probability density function you have a second moment? It's very simple. Let's calculate the second moment. Well, the first moment from symmetry is 0 because you have here this 0. So you can say from symmetry but you're right, there is a subtle issue here. I want to talk about the second moment where it's very clear. I want to do this integral. This is the second moment, right? By definition. And then you immediately see that for large x, this decays, as I already mentioned, like 1 over x squared, when x is much bigger than a. So what do you have here? You have x squared divided by x squared. All this junk goes to a constant for large x. And if it goes to a constant and then you integrate to infinity, you get infinity. Now, why is this not an obvious notion? These ideas that you have distributions with infinite variance, people, very clever people like Gauss, as far as I know, did not think about it. I know in mathematics the first guy who thought about was a guy called Cauchy, that you all heard from Cauchy, from infinitesimal. So it arrived rather late. And why is it difficult? Maybe because let's say you have some data. So let's say you have a data of some observable x. Even you take this distribution and let's say I somehow generate the random variables out of this distribution. I'm not explaining how exactly you do this, but we will see that later. But then I have a set of data points. So at the beginning I generate one, and let's say it's here. So let's say this scale is roughly 1. So I get some numbers, 0.52. This is measurement 1, 0.58, because this is most likely. Then maybe I get something a bit bigger here. 0.68, blah, blah, blah. And I will do that many, many times. So, and then you say, wait, what do you mean that the variance is infinite? Yeah. Let's take all these numbers. Let's say you have 1,000 numbers like this. And then let's define the variance like this. Sum over these measurements divided by n. This is the second moment, right? Is this the second moment? This guy, when n is finite, and any measurement is finite, you have, let's say, 1,000 if you are, you did a good experiment, you have 1,000 data points. This is some number. So this is a number, right? It's not infinite. So what do I mean by infinite? What will happen if I have this data? So first of all, this thing is what I call, this is not the variance. No, it's not obvious. This is the sample second moment. The word sample is important. If these random variables come from the Gaussian, in the limit where n becomes bigger and bigger and bigger, this will converge to the second moment of the Gaussian. If you take it from these fat tail distributions, it will converge to some it will be some kind of random number. What does it mean? You take n equal 1,000, you get one result. Then you increase n, you take it to 10,000, you get a different result, etc., etc. So the sample average never converges, and it just increases when you increase n in a random way. So in that sense, the sample average does not converge to the ensemble average. The ensemble average is infinity, which was defined here, this guy. But if you, let's say you do an experiment and you say, I always take 1,000 points, and I always measure the variance with 1,000 points, then I'll get some number. If I don't check this, the convergence, that is, I increase n, I will not notice that this guy is actually not converging to something. If I'll assume it exists and just, take my data, divide by n, you'll get some number, and then you'll say, oh, maybe it's like Gauss. And this will be wrong in this case. Okay, so there is a difference between the sample and the variance calculated from the PDF itself, in principle. So to see this a bit deeper, let us now look at the following. We very much like Fourier space. So Fourier space will be denoted by this symbol. So I have here k. K is the Fourier space, while before I had x. But you see, this is the reason why I have the capital X. So you see, this is the Fourier transform corresponding to the random variable related to x. That's why I had it before. Otherwise, I could have omitted this x here. But now it's kind of useful because it reminds me what this k is related to this x. And this is simply, by definition, integral from minus infinity to infinity, ei kx, p capital X, x dx. This guy, you can write it also in a different way. What is this? You see, you have some function here of x, which is this exponential. And what are you doing here? You are averaging over x. So I can also write it ei kx average. So these brackets are averages, and they just mean all this. You see, when I have these two averages, I save many symbols, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. These are only two. So the averages are useful if we understand what they mean. So this is it. Now, we all did many times the Gaussian case. So let us look at the Gaussian. Very simple. For a Gaussian PDF. So this is a simple exercise. You all did this exercise, for example, I think in quantum mechanics or in some analysis course. But let us just repeat it. Not because I'm interested in the Gaussian, I'm actually interested in this fat-tailed one, but we will show the difference between them. So let's take, for example, this normalized form. This is the normalization. I use here A. It's not related to this A, but it's a parameter I put inside. It's the width of the distribution. This is actually the variance, right? So this looks like simply like a Gaussian. And the width here is more or less A. So if I go to Fourier space, you all know there is a conservation rule that a Gaussian in X space remains a Gaussian in Fourier space. And so the Fourier transform, this tilde says it's Fourier transform of this same function is exponential k squared a squared divided by 2, if I remember correctly. Yeah, sure. So what do I do here? I simply take the Gaussian, I perform the Fourier transform, and I get a Gaussian. I don't do this in exercise because it's very simple and everyone here did it before, right? I mean, this is not new, right? Is this new for someone? Is it trivial? Is it not trivial? Okay. So this is very easy to prove that you get this Gaussian. So also in Fourier space it looks a Gaussian, but this is kind of a coincidence. Now, what will happen if I use the Lawrencium? So again, this guy is the Lawrencium. It has another name called Cauchy distribution, because Cauchy was the guy who found it. Physicists call it Lawrencium because if you look at, for example, the width of a transition, let's say you have an electronic transition in a hydrogen atom or whatever, the energy transition has a width. It's not a delta function. It has a width, and it's always fitted with Lawrencians. So this is just what I'm saying here. This Lawrencian function, if it's new for you, it's actually used to fit data in all the spectroscopy experiments, thousands of experiments. It's not a kind of rare function. It's very common. That's why we have the name Lawrence associated with it. Mathematicians call it Cauchy. And actually the mathematicians were first, but never mind. So if I have the Lawrencian, I get a different behavior. Well, this is not in the Fourier space. So I need to take this function. I need to multiply it by EI kx. And how do I solve this? I need to integrate from minus infinity to plus infinity. This will be an exercise for you guys. You get here two poles in the complex plane, because when x is plus or minus IA, you get a pole. And then if you understand complex analysis, you do the integration on the real line, but then you extend it above here, far away, and this integral will give you 0, but then you can use Cauchy formula with this pole, and this, when you do the integration I kx, will give you exponential decay. So after a simple exercise, pxk, so again, this is for the Lawrencian. Is this. This comes from these two poles. And you see A has units of length, if x is length. So you have k absolute value times a, and here you have k squared a squared. Of course, these two functions are very different, but how do they look in Fourier space? This guy looks like exponential decay. At k equals 0, this is 1. This is 0. So this is exponential decay on both sides because of this absolute value of k. This guy, how does it look? Well, it looks like a Gaussian. What is the most striking feature which is different here compared to here that you see or you don't see? Well, in what sense they are different? Very different. Of course, they are different, but at least for me it's obvious, but not for you maybe. Why are these guys very different? In what sense? See this cusp? What? I can't hear you. You're right. The derivative. Right, so I think what you're saying is that the derivative here is going down, the derivative here is going down, and then you have a discontinuity in the second derivative actually. You have a discontinuity in the derivative. In short, this point is non-analytical because of the absolute value of k. When you do this exercise at home, and this is because when k is positive, you'll find a pole up here if you close it here. And then if you take the opposite k, then you need to change close it differently or choose the pole slightly differently. So this is non-analytical. And this is the important point I want to emphasize. Non-analytical. What do I mean by non-analytical? Let's say I take this point, for example, and I perform a Taylor expansion around this point. Then what I get, if I continue this, I take all the terms around this point, I'll get a function that continues up here. So in that sense, it's non-analytical. When you expand around the point, you don't get the behavior here because this you just continue this function. This is simply e to the minus kx, and then it will diverge at k minus infinity. So we see here something non-analytical. And what we want to show now is that this non-analytical behavior is actually related to the fact that this guy, the Lawrencian, its second moment diverges. While here the second moment is finite. We'll start to understand this now, slowly, slowly. But it's general. If you have a power law distribution in general, some fat-tailed distribution that decays very slowly, like a power law, it may have this non-analytical behavior in k-space, and this is going to be important, and this is going to distinguish these set of distributions. This is just an example. Let us see why it's not surprising that we got this non-analytical behavior. From the point of view of the moments of the function. So what we were looking at in general, we have this p, x, and k. We call it sometimes the Fourier transform of px because it's the Fourier transform, but it's also have a second name. It's also called a moment generating function. It's very annoying that it has two names, but maybe there is a good reason for that. It's also called characteristic function, so it has 3 names. This is like doctors, they like to have complicated names so no one will understand them. Why is this the case? Let us look at this in general. We said this is the integral Ei kx px x dx. Great. Now we can Taylor expand this exponential, and then we'll get sum n from 0 to infinity, integral from minus infinity to infinity, I kx to the power n factorial. This is just the exponential with the sum. P x dx. This guy, what do I do now? I just do the integral x to the power n px dx. What is that? That's simply the moment, the nth moment. So I can write this as sum n equals 0 to infinity. I have here n factorial. I have I k to the power n. And here I have x to the power n. Let us look at the first few terms. N equals 0. N factorial is 1. This just gives you 1. What is the first guy? In general, it's I k x. And what is the second guy? It's I squared. That's minus 1. N factorial, when n is 2, is 2. The second moment. And then, of course, here you have all the other guys. The third moment, the fourth moment, until infinity. These are these dots. When I did all this, I assumed one thing. I assumed that these moments exist. It could be the Gaussian distribution, but not the Lawrencian. It can be many distributions, the uniform distribution, all these guys. I could use them, all of them have all the moments exist, so I can write down this expansion. What is this one? This one is, what is it? It's simply, we call it normalization. Simply said, if you take k equals 0, this is the first term in the expansion, the integral from minus infinity px dx by definition is 1. And that's why when I put here k equals 0, I get 1. I put here, in the Gaussian case, I put k equals 0, I get 1. Any distribution, any legitimate PDF at k equals 0 has to be 1, otherwise it's not normalized. If you did some calculation and you find some PDF in k space and you put k equals 0 and you get 22, you know you made a mistake. The first term is from this expansion, you get here k times the first moment. So why is this a moment generating function? I can take this function, here it's with tilde. Let's take the derivative with respect to k, px k, and then set k equals 0, and then also divide by 1 over I. Let's do this here. So instead of doing it inside here, I'm doing it on this infinite series. So when I take the derivative with respect to k of 1, what is it? It's 0. It goes away. When I take derivative with respect to k, I get I times the average, and then I divide by I. Then I get here the mean. When I take the derivative with respect to k squared, this will give you k. Right? So k to the power 2, you take the derivative, you get k. But now I take k equals 0. That means that by taking k equals 0, I'll kill this term. I have a k to the power 22. I take the derivative as k to the power 21. But k equals 0, then it goes away. So here I have a method to get these moments. Now, maybe for you it seems a bit silly method. Why silly? I could take, to calculate the average, I could put here x and calculate the average. But many times, it's easier to find first the Fourier transform, And then you take the derivatives, and what's good about the derivatives, you simply expand it. And where are we actually expanding it, right? Where are we expanding it? Is k big or small? This is expansion when k is small. Corresponding to this region, but not for this case, but for a case where you do have an expansion around k equals 0. We are doing this, for example, for the Gaussian. So we are expanding here. So we have some distribution in k space. And when you expand it around k equals 0, it gives you all the information on the moments of the process. Now we understand why for the Lawrencium we had to get a non-analytical behavior. This is the bonus. Because if you had an analytical behavior, the second moment, for example, would be finite, but we know it's infinite. That's the main point of all this long discussion. So it's not a surprise that for the Lawrencium, the small k expansion is non-analytical, because if it would be analytical, you would have moments, and that we know is not true. But let us just write it, what I'm saying now. So let us say, for the Lawrencium, again, I'm working in k space. Absolute value A. What is the expansion? Is 1 minus k absolute value A. Of course, there are more terms. Now let us calculate the second moment. But if you think about it a little bit, the second derivative of absolute value of k, this will give you infinity. Because when k is positive, I say the derivative is 1. When it's negative, the derivative is minus 1. And then there's a jump. And then you blow up. And the second derivative will diverge. And that means second moment is infinity. Now, through this example, we understand, or we are starting to understand the general thing. This is the way you usually think progress. We have one simple example, which we can work out completely. This is the Lawrencium. We can calculate the Fourier transform. We can calculate the moments. We can do everything. Why can we do everything? Because we can do the Fourier transform. So it's easy. But it shows you possibly that there is some general trend. And this argument is very general, because it says any distribution function that in a real space decays like a power law in such a way that, let's say, the second moment is diverging, has to have a non-analytical behavior in k space. Because if it would, the second moment would be finite. So we are starting to see some mathematical beauty around this, and this is what Paul Levy started to understand. And this is how we started to develop the generalization of the central limit theorem. So we have two types of limit theorems. One of them related to Gauss and de Moivre, which is the old stuff. And another one which is related to these distributions, these finite distributions which have power laws. And this is what we are going to discuss after the break. I'll just derive you again the Gauss central limit theorem, and I'll derive you maybe for the first time, or maybe you saw it somewhere else. I'll derive you the central limit theorem due to Paul Levy. This was what we do after the break. So first thing we want to do is demonstrate this relation between non-analytical behavior and the divergence of moments. And I would like also to extend slightly what I did in the previous class. So far I looked at distributions which were symmetric about the mean. They were symmetric, plus x and minus x were the same. And actually that's the reason why the Fourier transform was actually real, because in general it doesn't have to be real. Now I want to consider one-sided distributions, one-sided PDFs, and you will see later that these class are also very important. So, and I'll denote the random variable by capital T. So Pt of t, so t, capital T from time, because usually time is not negative. That's why I use this, or temperature is also not negative. So I use this notation. So I think about some function, pt of tau. Very well-known example is, for example, the exponential distribution. So here you have 0. The random variable is 0 for negative t. So for example, exponential of t, this PDF appears naturally. For example, the waiting time between emission of radioactive emissions, it's related to something called Poisson statistics, which is very familiar. So many times this distribution is used. It's very famous. But we can have, of course, also other distributions which are fat-tailed. And for example, let's say you have a distribution that goes here like t minus 3 over 2 for large t. The behavior here, for our discussion, is not so important. Because if we are interested in the question, does the moment of this function, does it exist or not? What is important? The large t limit, the large times. The small t is not so important for the question, does it exist or does it not exist? It doesn't mean that what happens here is not important. Specifically for this question, is the average t finite or infinite? What you care about is the far tail, because to get the first moment, you just need to take this distribution and integrate over t, and then the far tail will be the convergence problem, always. It's not trivial why the small t is not important, but because of normalization, you ensure that you are normalized. So if I give you a pt of t, and I say this behaves like t to the minus 3 when t goes to 0, this is not legitimate, because this is not normalized at small t. So this is why when you look at the moments, you only care about what happens far away. Because of normalization, I always assume you can normalize. There's no issue with the small t limit, never. In this discussion, at least. Now, why do I introduce these one-sided PDFs? Because for them, it's very convenient to define another moment-generating function, which is this guy. So this is a moment-generating function, but now in Laplace space. So sometimes I would work with Fourier transforms, and sometimes I work with Laplace transforms. When do I choose which one? This depends on the properties of the random variable at hand, but both of them are convenient, and when you have one-sided distribution, it turns out to be very convenient to work with the Laplace transforms. Exactly like what we did before, we had the Fourier transforms. So the bottom line is, you need to know something about Fourier transform, you need to know something about Laplace transforms in order to understand this course. What is this guy? As before, this is simply the integral from 0 now, because it's one-sided to infinity, e to the minus u t pt t dt. By definition, this is the meaning of these averages. I take this function, and you see this is the Laplace transform of this function, exponential minus ut. This in turn I can write, this in turn you can see, I hope, is also a moment generating function. And I will also, you can write it also like this, pt hat u. So you see that we have here pairs. T goes with u. T is the real time, u is the Laplace space. So I did the Laplace transform, and now I have a function of u, but I still leave this capital T here so that you will remember what it was in the origin.
What do you mean when you wrote T is either finite or infinite?
That you have classes of distributions, that I want to define the world based on two classes. those distributions that have a finite first moment and those that have infinite first moment. Of course, you can ask, what about those who have variance, which is infinite, but first moment finite? But the discussion here will be to distinguish between these two guys in the same way, very similar to what we did before with the Fourier transform. Okay, so these are just the definition, but I can also write this. Now it's easy. This is just repetition in some sense. I can write it in principle as a sum from 0 to infinity. I just write this as a Taylor series, assuming that the series is converging. So I have here integral from 0 to infinity minus u t to the power n factorial e minus ut dt. Sorry. P, whatever this function is, I'm not specifying it. But when I write this series, what do I mean? I mean actually that all the moments actually exist. Assume that all these guys exist, then I have here sum n from 0 to infinity minus u to the power n factorial. And here I have t to the power n. You see the nth moment of this random variable t. Because you have here t to the power n, the probability density of t. When you integrate, you get this moment to the power n. And I have here an infinite series. How does this infinite series behave? The leading term, when n is equal 0, you get here simply, you get here 1. T to the power 0 is 1. 1 average is 1. You get this 1. What is this 1 again? This is like before. It's the normalization. I didn't specify nearly nothing except for the fact that the moments of these guys exist. But you know something on the Laplace transform of this function, that when u is equal 0, you get 0. And this is very obvious, because if u is equal 0, then you just get the integral. The function was 0 for negative, so this has to be 1. And the leading term is u absolute value t. And the next term is u squared over 2 t squared, blah, blah, blah. These are all the higher order moments. So now you see that the same as before, that this is a moment generating function. Why? Because now I can take the derivative with respect to u, with respect to the Laplace variable, take the Laplace variable to be 0. This is a mistake. And then get, for example, the first moment. So for example, let's write it here. This is only for normal cases where the moments exist. For example, the second derivative, the first derivative of p, t, and u, this Laplace transform, when u is equal 0, with a negative sign because of this minus here. This minus comes from this minus, and this minus was important for the integral to converge, of course. U is positive. That's the way at least I think about it. This is equal to the mean. So pt and u is the moment is at the moment generating function. In this case, so when we say moment generating function, sometimes it's in Fourier space with k, and sometimes it's in Laplace space, depending on whether or not the distribution is two-sided or one-sided, etc., etc. Of course, you could take the second derivative. It's the same trick as before. They take the second derivative with respect to u. You'll get the second moment. If you get the second moment, you take u to 0. All the higher order guys will be 0 when you take u to 0. So when I say this, I mean also similarly for tau to the power n. Now, of course, what we want to do is work with cases where this usual behavior doesn't work, in the sense that we want to look at a fat tail distribution. So let us look at one example first and then do it slightly more general. So let us look at an example. Pt and t is equal to 2 square root of pi t to the minus 3 over 2 exponential minus 1 over 4t. This is only for t greater than 0. This PDF, you see at small t, this is 1 minus something very small. This is very big, so this goes to 0. And then at very large t, this decays like t to the minus 3 over 2, this guy here. So what do we understand? I hope you understand. What is the first moment here? What is the first moment? It diverges, right? Simply because the integral until infinity of something that eventually goes like 3 over 2 times t dt. I'm not writing the other junk. T to the minus half dt. When you do the integral, it's t to the plus half. That is infinite. So the decay here is so slow, it's such a fat tail that the first moment doesn't exist. It's not the variance now, it's the first moment. So if you work this is going to be for your exercise at home. What is the Laplace transform of this? So a simple exercise, I multiplied it by exponential minus ut, integrate. You'll do it at home. You will get this answer if you do it correctly. You have a u to the power half. Remember, u is positive. This is also a non-analytical behavior. So this is our second example. The expansion here for small u u to 0. Is this surprising or not? Not so surprising, but we are starting to see a rule. Why did we have to find here u to the half? Let's say you add here u, then you'll get a first moment. The derivative of u to the power half, what is it? It's u to the minus half. Take u equals 0, you get infinity. That is the divergence of the first moment. So if you just blindly use this equation, take the derivative of u, take u to 0. Here you have u to the power half. You take it, you get infinity. But you know that's true because the moment diverges. So this is again a non-analytical behavior. And we feel it is because of the fat tail of the PDF in this example and similar in the previous example. And we also see here, when we say fat tail, we mean of the PDF, not in Laplace space, it's the large T. So another thing that we see here, we go to large T, and this somehow corresponds to small u. Small u is non-analytical, large T is a power law in these examples. So now let us see that this is indeed the case, and let's see it a bit more generally based on these simple examples. Why are they simple? I choose a very specific example. This PDF is kind of known for the expert. It's called Smirnov PDF. It's also a Levy PDF. It belongs to a special family of functions. So this is a very special example where I can perform the Laplace transform. Generally speaking, it's not easy to perform the Laplace transform. I'm not saying that this is easy in general. If I have some distribution, it can be very difficult. Of course, what you do today, you put it in Mathematica, and it either gives you the answer or not. And then if it does, then you good, and if not, not. But or you go to some table, etc. But most cases, we cannot say exactly what is the Laplace transform. But it's not so bad because we can always do things numerically. So, okay, so now let us see that this is general and be more specific for the theorem. So the theorem deals with the following question. If we have a PDF that decays like a power law for large t, how does it behave for small u? These type of theorems are called Tauberian and Abelian theorems. So we will consider the following. Let p t tau decay like some a t minus 1 plus alpha. So here I'm just plotting, I'm just saying that the PDF in real time t decays like a power law. A, what is a? It's some number, some coefficient which is specific to this function. We know one thing about A is positive, otherwise this PDF is going to be not a kosher one. Alpha in this discussion now is going to be between 1, less than 1, bigger than 0, which means that, as I said before, the average of t is now diverging, because again, if I multiply this by t and do the integration, if alpha is less than 1, the integral will be infinite. There's no moment. So I'm considering here many different types of functions actually. For example, this function, t to the minus 1.2, or maybe this function, t to the minus 3 over 2, etc., etc. All this large family of functions that don't have a moment. Why does alpha need to be bigger than 1? What would happen if alpha would be, let's say, minus half? It will not be normalizable. So you have to decay at least as fast as minus 1 plus something positive. Otherwise, the integral itself would diverge without, the zeros moment would diverge, and that's not a PDF. So we assume this condition. And now the question is, you have the Laplace transform of this guy. So how does this behave? Can you guess for small u? I said it a few times. So when u is equal to 0, it has to be 1. And here, I want to know how it behaves. What is the correction to 1? If this distribution had a moment, what would you have here? You'd have here simply u times the average. That was before here. So for normal case, even if alpha is bigger than 1, which means that the first moment is finite, then we have phi t and u is 1 minus u average t. So, and then of course there are many other terms which I'm not going to discuss, again for small u. So in some sense what will appear here is actually in some sense replacing the average in some sense. But it will depend, that's part of the nice thing, it will depend on what? It will depend only on the details written here on the blackboard, only on A and alpha. And in that sense, it doesn't matter what is this distribution. It can behave in many different ways. Its small u expansion, if it has this power law tail, will behave according to a law that we're going to discuss. And we also understand one more thing. Here we expect something non-analytical. U to some power. Can you guess what is the power? You could from the example. What was the power here? What is alpha here? What is alpha here? Half. And what was the u? Half. So, okay, we can guess. There's a number here. This number must depend on A and maybe also on alpha. Okay, let's more or less calculate and prove this. It's not so difficult to do. So to do it, all we need to do, well, not rigorously, God forbid. We are not mathematicians, but the final result is correct. What do we want to do? We want to integrate E u t p t t dt. And the way I'm going to do this is the following. I'm going to say, I have an integration from 0 to infinity. I'm going to integrate from 0 to some t0, e to the minus ut ptt dt, plus integral from t0 till infinity a t minus 1 plus alpha e u t dt plus some epsilon. Well, when I write plus some epsilon, it's obvious, but what is this t0? I assume, for the simplification of things, that there exists some t0, let's say here, that this expression is exact. And then this epsilon will be 0. I'm not going to discuss this small epsilon. There was always some big T0 in such a way that this is a good approximation for the PDF itself. This is what I'm doing here. But if you want to do it more rigorously, then you need to calculate also the correction. So what I'm doing here, I'm saying the following. There is a tail. Here is my tail. Maybe there's also a correction to the tail. I could include it also and show it's a smaller term, but I don't do that because it will take some more time. So I say there is some epsilon, and then eventually I say there is a t0, and this function is exactly this power law beyond this t0. So t0 is some fixed but large number. Okay, this is the idea here in this proof. So we are going to rewrite this in the following way. I'm going to rewrite this as integral from 0 to t0 e to the minus ut, what do I want to write, dt plus integral from t0 till infinity a t to the minus 1 plus alpha dt I'll soon explain, plus a integral from t0 till infinity eut minus 1 t to the minus 1 plus alpha plus epsilon, which again in our approximation, if the function is exactly this function beyond t0, this guy is actually 0. So what did I do here? Soon you'll understand why I did it, but what did I do here is something very simple. You see, I took this term, it has a plus, and I have here a minus. So I just added a term and subtracted the term. Soon you'll see why I do it, because This minus 1 will allow me to do the integral eventually, otherwise it will not converge. It's a trick. But for now, what I did is I added something and I subtracted something. That's all. That's why you have this minus here. Now, I'm interested in the small u limit. So let us consider this part first. How does this behave at small u? Well, you see this integral for small u, it's perfectly, everything is perfectly convergent. If you want to think about, one way to think about it is, let's expand this function in the Taylor series, but you have an integration not till infinity, you have an integration until some t0, let's say 10 to the 1 billion or whatever. This integral is perfectly analytical. You have here a Taylor series coming out of this. So you will have here a correction which is of order u, not order u to some power alpha. And for small u, when u is equal 0, this is going to be a constant. So importantly, the important fact here is that here we have, when u is equal 0, this is more or less 1 plus u times something. And I don't care what is something. Why don't I care? Because I'm looking at u, which is small, and this term will give you this will only be a correction, because here I'll get something small, I'll get u to the power alpha. That's the idea. So eventually I can throw this guy away, I don't care about it. Why is this simply the normalization? Is this clear to everyone, this idea? More or less. So now I need to treat this guy. So this we'll do on the side. Of course, what is the goal now? The goal is actually to get rid of this t0, because what is this t0? It's just something I put in order for it to vanish somehow. So I have this integral. I need to do this integral. It's a simple thing. t0 till infinity, e to the ut minus 1, t to the minus 1 plus alpha, d tau. And again, where do I need to do this? I need to do this when u is small. I only care about small u corresponding to large t in the real time. So for that, I will, of course, the homework, which I will announce maybe next week.
Why is it gamma function? You have the minus 1.
It's a gamma function when you change integrals. You can. What do you mean? Why is it a gamma function?
Because יש את המינוס אחד המונה.
Yeah, but you need to. Without this one, it's not a gamma function. It diverges. So you need to write it as the derivative of x to the minus alpha, and then do integration by parts. You understand? Without this, it diverges. So you need to write this as d over dx of x to the minus alpha, then do the integration by part, and then you get rid of the 1, but you are then with an alpha. You see this or not? No, it's trivial. I mean, you write it like this. E to the minus x minus 1, d over dx, x to the minus alpha, dx. To get this 1 plus alpha, then you need to divide by alpha, whatever. And then you take the derivative here, you get rid of the 1. Then you get the same integral, but instead of 1 plus alpha, you get now with a minus alpha. This integral exists, and it's a gamma function. It's integration by parts. It's trivial. So this is for the Laplace transforms, but now assume you have symmetric PDF what I called before X space, and a symmetric means that Px x is equal Px minus x. For example, the Lawrencium that I had before. So this is the 0. This function is symmetric with respect to x. It has this parallel tail. And let us assume that this PDF in X space goes like some A, not related to the A before, x1 plus mu. And mu is some exponent between 0 and 2. We will later need to see the physics. What is this mu? This is not physics, this is math. So you have some exponent. For example, for the Lawrencium, this mu is 1. Why 2 here? Well, this is because if you have here 3, the second moment is finite. And it's very important for us here that the second moment is diverging. So here, the second moment is infinite. Then, and again, when this I plot this thing, it means in the limit of large x. So this is the far tail. I don't care what happens here in the middle. The Fourier transform and the Fourier transform is for small k because large x goes with small k. This goes like 1. The 1 is simply normalization. When k is equal to 0, you are normalized. And then you have a non-analytical term. And this non-analytical term has some k to some power. Can you guess the power? It's pretty easy now, I think. Or not? What is the power? Mu. We saw this in an example. When it was a Lawrencium, we had here 1. And again, of course, this non-analytical behavior is again this diverging of the second moment. So if I take the derivative and mu is less than 2, then the second moment will diverge. If mu would be bigger than 2, actually you can, this will also be homework. One can show that if you have 1 minus k to the power, let's say 3, and this is the first order correction, then the PDF itself is negative, which means it's not PDF itself. So mu has to be less than 2. It cannot be bigger than 2 if this is the leading term. And here you have some prefactor, A tilde. A tilde is related to A and to mu, like this coefficient here was related to alpha and to A. And in your homework, you're going to find what is A tilde. It's related to some sines and some gamma functions and some simple integral. Okay, I suggest we continue unless you really want to break now. And then I'll release you a bit before the time. What do you say? Are you dead tired or? It's okay? No objection? You're not falling asleep yet? Great achievement. If you eat, then you're tired, then you'll fall asleep. So now let us reach the main part of this lesson, which is the central limit theorem. And I'll start with the Gaussian one, and then we'll do the Levy one. So the Gaussian central limit theorem CLT is central limit theorem. The reason why it's called central is actually not because it's of central importance. It's because it's valid in the center of the sums. So this problem says the following. Let us just state it. let x1, x2, xn be IID random variables. I told you what these means. Independent, identically distributed random variables. So there's no correlations between all these guys. They have a common distribution. P. Maybe I should, how did I symbolize these? Independent, there's no correlations. Identically distribution, so all of them come from the same distribution. There's one distribution for all of them. You can have situations where the first 20 have one distribution, the next guys have a different distribution. You can have many things. With common PDF, I'll just write it like this, not with a capital X. I will assume, however, with zero mean, which means that the average of x is 0. And the most important assumption maybe is, and the variance sigma squared is finite. So because the mean is 0, the variance is actually the second moment, and I assume it is finite. But the beauty of all this central limit theorem is that besides this, I don't assume much on this function. It can be any function, as long as it is a PDF, positive, normalized, and possesses the second moment. Then let Z be a sum of these xi's and divide them by n to the half. So I don't take one guy or two guys, I take many, many guys, and I think about the problem in the limit where the number n is going to infinity. What is this? This describes a random walker. You have a random walker, you jump to the left or to the right, we have some distribution. The size of the steps can be random themselves. So this is actually a random walk in some sense, with a continuous distribution possibly of these xi's. So this PDF of x can be anything, practically anything, which has a first moment. It can be this uniform distribution. It has to have zero mean only for simplicity. It's very easy to do the same when this mean is not 0. It's just a shift, so I'm not doing this. So the PDF can be Gaussian. This PDF can be exponential. It can be two delta functions. And you can imagine an infinite number of distributions. But this sum, which in principle depends on n, then the magic is, the magic that you know, the PDF of z. So the PDF of z in the limit n to infinity is simply a Gaussian. So I'll write it like this. It goes to means in the limit where n is big. 2 pi square root sigma exponential minus z squared over 2 sigma. So it means that you take on your computer some random variables, let's say from uniform distribution, you sum 1,000 of them, you divide by n to the half, you do it one time, you do it many times, and then one after the other, and then you plot the histogram of this random variable, you'll get a Gaussian. You do it the same with this distribution, you'll get a Gaussian. You do it with this distribution, you'll get a Gaussian. And this is what I said before, that all these guys, in this sense, are attracted to the normal distribution. So this guy is like a fixed point, if you know what's a fixed point. Everyone is attracted to him, everyone loves him, everyone goes to him, provided that you have the second moment. This is why this distribution is damn important. This is why, for example, diffusion equation, you take particles, you put them in space, if you want physics, you put them in space and you let them spread. Now we understand they will spread like if they don't interact and there's no external forces or there's no drifts, they will spread like this Gaussian law. And this scaling is the scaling of diffusion, if so-called. What will be n when we talk about particles like Brownian particles spreading in space, what is n? What is the physical meaning of n? When you have Brownian particles that spread like a Gaussian, like in diffusion, what is n? Time. So as time goes by, the width of this guy actually increases. So this will be like time. So you need to know how to jump from the mathematics to the physics, but it's actually the same. And here I would say the mathematics is more important than the physics because it's pretty well stated here. Now let us prove this limit theorem. Not because you don't know this, you should know this, I think. It's just simply that once you understand this proof, then you immediately see the other proof. So first of all, so the proof, don't tell mathematicians that I call it proof. So I first have the distribution of x in Fourier space. You'll soon see why it's so convenient to work in Fourier space, because I'm considering the sum. If I don't do it in Fourier space, it's possible, but it's not something very pleasant. So first of all, we look at Fourier space, and I know the small k limit. I know because I spent the time on this, and the small k limit in general behaves like ikx minus k squared x squared over 2, and here I have a term with a k3 times some coefficient, which is the third moment, etc., 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 etc. In our specific example, what is the average x? Is 0. So it's 1 minus k squared sigma squared over 2. And then you have all kinds of other terms that they are important. We should think about them because we actually want to show that these higher order terms, when we consider z, are not important. Why? Because let's say the coefficient of the third, k to the 3, is something to do with the PDF, which is different for every PDF. It's not universal. This is general. Of course, what is sigma? It depends on what is your PDF. But we want to show that these k to the power 3, k to the power 4, k to the power 22 are not important in the limit n goes to infinity. And how is this done? Now, what we really care about is this PDF of z. And we are interested in this guy in k space, where things become easy. So what is this function? Well, we said it already, but let's repeat. It's the integral from minus infinity to infinity, ei kz pz of z dz. But this is not really helpful because we're actually looking for this function. We don't know this function. Well, we do, but we are pretending that we don't. This function goes to a Gaussian. Now, I'm not going to prove that this is going to a Gaussian. I'm going to prove something that is totally equivalent. I'm going to prove that this guy goes to a Gaussian in k space. And if this guy goes to a Gaussian in k space, then this guy, by the inverse Fourier transform, also goes to Gaussian in k space. But again, this is not useful. This is definition. On the other hand, I can also write this more explicitly. I can write it as Let us do it as we did before, EIKZ average. It's just this and average. You see it's the same thing. Now I think a little bit more, and then I say, okay, but what is this Z? This Z is written down here. So I can write it like this, an average of EIK, and just I plug in the definition. I still didn't do much. X over n to the half, average, xi. Now, because it's the first time you're doing such thing, or maybe the 20th time, doesn't really matter, I can write it slightly. So here I have x1, I divide by n to the half. Here I have EIK x2 divided by n to the half. EIK n to the half, and I need to average. So what I did, very simple, I just wrote this sum in a stupid way as an exponential just for clarification. But now I think a little bit, and I understand why is it super important that these guys are not correlated. This guy, you have the random variable x1 here, this guy has x2, x3, x4, up till xn. But they are independent. So, and when I average, what I actually do is I replace this into this average, which can be of this guy if I knew it. I replace it with the integral of x1 times the PDF of x1, the integral of x2 times the PDF of x2, etc., etc. This is what I'm doing here. So this average also means p x1 dx1 p x2 dx2. And I have here n integrals with all these exponents here. And then because they are independent, I can take one of them. And then I have px x e I k x to the power n to the power half dx. All this to the power of what? N. Why? Because I have n terms and they are independent. So I took one of them, and this guy, when you average, is the same. So I have to take this to the power n. This, by the way, is a totally exact expression. In principle, let's say you want to look at the sum of these random variables, but let's say n is equal to 20. Let's say you know the Fourier transform of this guy. You have this Fourier transform, you take it to the power 20, and you do, let's say numerically, you inverse Fourier transform, you can get the exact result, which is not Gaussian because n is a finite number. When n goes bigger and bigger, it will become a Gaussian. Okay, so up to now we didn't do much. But now what I'm going to exploit, what I did not use so far, is the fact that n is very big. So now I'm going to use that fact when n is very big. I also see something here. You see that the k, this is Fourier transform with respect to x, but so to say with a k, which is not k, but k divided by n to the half. You see, this is actually the kind of a new Fourier variable. K divided by n to the half. So I can also write this as a different way, p of x, k to the power n to the half to power n. And this is in Fourier space, where the Fourier variable is kn to the half, not k. Now you understand what's going on here. When n goes to infinity, k over n to the half is going to be a small number. That's why the small k on the original Fourier transform is going to be important. So let us be slightly more specific. I have px of k. I added already on the blackboard, but now I'm going to be more specific. I'm going to write it as sigma squared k squared over 2 plus k, what do I want to write? K to some power alpha, a, some power gamma. What is this gamma? Anything that is bigger than 2. If the function is analytical, gamma, for example, can be 4 or 3, whatever, some correction. And again, what is my goal is to show this is eventually not important. In the limit n to infinity of this problem. And of course, there are many more terms. So, but this is the first correction that I'm going to show that is negligible. Then all I need to do is plug this into this, taking the fact that k is small, and then I have the following, that I have for z, p zn in Fourier space of k, this is what I started with, this guy, is equal to 1. I'm just using now the expansion of this guy, using that, with the fact that n is very big. So I add here k to the 2, but I had to divide by square root of n, and this is why I get here the n. This n is very important. And this is why when I add k to the alpha, I divide it by square root, so I have gamma over 2. Importantly, when n is big, this is small. This correction term is obviously small because gamma is bigger than 2. And then, of course, I have many more terms, and all this to the power n. Now you understand, or maybe you have the intuition from physics, why I divided by n to the half. The whole goal was to get this n. I have something divided by n, and here I have to the power of n. So what is this guy in the limit? This is by definition the exponent. So in the limit, this is nothing but sigma squared k squared divided by 2. In particular, when you take the limit, this term is not important. This is negligible in the limit. If n is big but finite, sometimes we leave this term and get the correction to the Gaussian. This is possible. This is something called Edgeworth expansion. We will discuss about this. So if n is finite, we must take into consideration to see how do we correct the central limit theorem. The central limit theorem is an approximation in the sense that it is valid only for infinitely large n in the limit. Then, of course, immediately we get the PDF of Z is Gaussian. Mathematicians develop many theorems and many precise definition. What does it mean to converge? You can see in my notebooks, for example, there's something called Barrier-Sin theorem that tells you how far you are from the central limit theorem when n is big. So there's really gigantic work in mathematics on corrections, and I'm not going to go into this detail. Instead of, I want to bring you now roughly to 1930 to the work of Paul Levy. So now we want to generalize this. What happens when the variance is diverging? Obviously, this doesn't work. So Paul Lévy was a French mathematician. He, together with some Russian mathematicians, developed all these central limit theorems, but today they are called, these distributions that replace the Gaussian are called Lévy distributions. He was lucky he had one very famous student. The famous student was a guy called Benoit Mandelbrot. Mandelbrot was the father of fractals. But everything I'm telling you here is obviously fractals. So I'm telling you about fractals in the most boring way. But soon you will see why these are fractals. But this is the way Lévy introduced them. And maybe some of you see the fractality here, and some of you don't, and some of you don't know what is a fractal. But this is a fractal, actually. This is the first fractal in nature, in mathematics. And we will see maybe next lesson why this is a fractal. So what did Paul Lévy do? I want to define, let the same way as before, Zn, or nearly the same way, sum over xi till n to the power some, 1 over gamma. This gamma is not related to previous gamma. Gamma is reset now. Nothing to do with this gamma. He wanted to consider this sum. Before we put here 2, right? In order to get the Gauss central limit theorem. But now we're dealing with a new case. So at the beginning we don't know what gamma is, but soon we will say what exactly is gamma. And he wanted to consider this for PDFs. We're going to consider symmetric PDFs. So P of x is symmetric. But the second moment is infinite. So Gauss is not valid. So we know that this happens when P of x decays for large x like minus 1 plus mu. Mu is something between 0 and 2. And there is a coefficient here, which I'll not write. But we can write it, but it's not so important. This I'll leave for a homework assumption. So again, if you have this type of distribution, mu is between 0 and 2, the second moment is infinity, as I explained already. And then the central limit theorem doesn't work. Okay, but what does work? We don't care about things that don't work, we care about things that do work. So he said maybe we can look at this sum and rescale it differently than what the Gauss did and get some central limit theorem. In this case, what do we know about the Fourier transform? This is what I already explained, and now you understand why. Pk of x of one of the guys, I'm not treating yet z, soon I'm going to discuss z, the sum of many. This goes like 1 minus some a tilde k to the power mu. Again, when k goes to 0. So this is the non-analytical behavior. For example, for the Lawrencium, mu is equal 1. And this non-analytical behavior shows that the moments are diverging. Now what I'm going to do is essentially do exactly the same thing as I did before and get a generalization of the central limit theorem. What do I want to do? I want to consider P of z. But I know now I want to do it in Fourier space. Why do I want to do it in Fourier space? Because then the summation turns into simply taking the distributions to the power n, and things become super easy. So I'm looking, you're already expert in this notation, it's the PDF of the sum in Fourier space, that's why you have the tilde. This guy, these are still independent IID random variables. So using the fact that xi are IID when I do the sum, I can treat the Fourier transform of this guy, the Fourier transform of the other guy, just multiply them and then take it to the power n. They are all the same. So exactly like before, what will I get? I get here 1 minus a tilde, this guy, k to the power mu, all this to the power n. But now k, when I add each one of these terms, I need to divide the k with n to the 1 over alpha. So I'm going to write it here, mu over gamma. And these are the correction terms. Like before, they are correction terms because this guy gives you this guy, but there are higher order terms here which will vanish like before. Now I know one thing. What is the gamma that I need to choose? What is the gamma I need to choose? Let us choose gamma equal mu. Why does it make sense? What is the Gaussian case? The Gaussian case, what is this mu? It's 2. Why is it 2? Because this is the second moment. This is the analytical expression, mu equal 2. And then the scaling is n 1/2. So you see that when mu is equal to, we get back Gaussian, and then gamma is of course equal to. But generally speaking, we're going to choose gamma equal to. Then what do I get here, and why do I do this? Mu over gamma is simply 1. Then I get in the limit pz of k, when n goes to infinity, one a tilde k to the power mu divided by n to the power of n. And what is this? This is by definition the exponential. So this is simply exponential a tilde k to the power mu. These distributions, which are written here in Fourier space. Now you need to take the inverse Fourier transform and you get some distribution. So the inverse Fourier transform gives a PDF called today stable distributions or Levy distributions. These are not the most general distributions. Why? Because I assumed here that you have symmetry. They are more general class of Levy distribution, but these are the symmetric Levy distributions. Unlike the Gaussian, I cannot write explicitly in real space, in terms of simple functions, what is this Levy distribution. But this is a lie. What do you mean? What do I mean by that? If you go to Mathematica and you ask Levy distribution with index mu, it will give you the answer. So these are tabulated functions. How do you need to think about them? These are exactly like Gaussians. And we know everything about these functions, even though we cannot express them in terms of functions that you know up to now. Or to put it differently, the inverse Fourier transform of these functions from now on are called Levy distributions. They are tabulated and they are as famous as the Gaussian. Of course, maybe this is not so satisfactory, so we need to investigate the inverse Fourier transform of these functions. So how do they look? Or before that, what did I actually say? Here, before I said there's an infinite number of distributions which have a second moment which are attracted to the Gaussian. Now I say something similar but slightly different. There's an infinite number of functions that are attracted to Levy function, but there's not one Levy function in some sense, because this depends on this mu. So there's a whole wide family of functions depending on mu. This parameter is also important, but it's somewhat similar to the width that you have here. But it's also different, because this A, where does it come from? It comes from only from the power law tail. So we have the following general picture. We have for the xi's all kinds of distributions. But let us consider a specific decay like x to the minus 2. So this is a PDF that decay like x to minus 2, but here in the middle it's 0. This is the PDF of the microscopical variable of the distribution of the sum. Then you have another one I can plot. These are all normalized functions, maybe look like this. Again, with x to the minus 2, and the prefactor here and here are the same. And then you have another one which might look like this. No matter, you take random variables from these distributions, you sum many of them, you rescale correctly now with this parameter, in this case mu is equal 1. You sum many and you plot histograms, and what do you get at the end? You get this distribution with the corresponding mu. Mu here is 1. By the way, if mu is 1, what is this distribution? This is the Lawrencium. So the Lawrencium that I introduced at the beginning is a very special Levy function. So we know something about the Levy distributions. If mu is equal 1, it's a Lawrencium. If mu is equal 3 over 2, it's called something else. It's called Holtzmark. And all of them are known, all of them tabulated. So what we see here, that all these guys are attracted to the Lawrencium. Exactly like before, that all the functions with the second moment were attracted to the Gaussian. The difference is that if instead of 2 I add a 3 over 2, I'll have a different function. But it's general function, and it's called the Levy function. So how do the Levy functions behave, more or less? Again, they are tabulated. You can go to Mathematica and you can view them. All their properties are known. They are also in my notebooks a little bit about this. So we start, one special case is, of course, the Gaussian. That is mu equal 2. You see, the Levy distributions, as a special case, when mu is equal to, include the Gauss case. That's when the second moment is finite, you're Gaussian. So in this sense, it's really a generalization of the Gauss central limit theorem. The Gauss case is the only case where the PDF does not have power law distribution, does not have fat tail distribution. It doesn't decay like a power law. And generally speaking, what you will see is something like this. I plot here, you see the tails, which are fatter, because this decays like a Gaussian. It's very small probability to find a particle. But generally, these Levy distributions, not surprisingly, also have a power law tail, like the original PDF. So the original PDFs all had power law, but they looked very strange at the beginning. They were non-universal. When you sum many, they go to this universal distribution, which has the same property as this guy, the same power law, but it is smooth. It doesn't have this structure, for example, or this flatness. Again, when you sum many, many, many random variables. How many? That depends on the problem. It can be 22. It gives you good approximation. It can be 2 billion. This is can be very delicate, depending on the example and what is mu, for example. So I'm not talking about convergence at all. Now, I didn't say much what exactly is this A tilde. A tilde is related to this power law at large x, to this A. The relation between A tilde and A is homework. Okay, so I'll take another 5 minutes to show you how this becomes interesting. Or maybe it is already interesting, or why this is a fractal. Do you know what is a fractal? It's not so clear, but we call it a fractal because Mandelbrot was clever. Well, roughly speaking, a fractal is an object that looks the same on all scales, or on many scales, and it has no typical scale. Okay, if you didn't understand, it's fine. In what sense this is a fractal? These Levy distributions are fractals because they don't have a scale. What do I mean by these words? The second moment does not exist. That means there's no typical length scale compared to the Gaussian central limit theorem. It also, the sum of these guys look the same as the one component of them. Why? Because let's say I want to take two random variables, I equal 1 to 2, and these guys are exactly Levy distributed. Then if I take EIKX, and they are IID independent of each other, this is IKX1 times EIK x2. Now let us assume that these guys are Levy exactly, not fat tail. These are exactly Levy distributed. What does this mean? This guy is maybe k to the mu, this first guy, and this guy is the same. They are the same. And this guy is e to the minus 2k to the mu. So what do you see here? The sum of two guys have the same distribution as one of the guys, of course, except for this 2 here, because you sum 2. That's what I mean, that one guy looks like two guys, and two guys look like 4 guys, and 5 guys look like 10 guys. That's a fractal. You can zoom in. This is a boring mathematician. He was so boring. That's why I bored you so much. The Paul Levy said no one, when he wrote all these things, no one paid any attention to this. But then Mandelbrot was his student. He had one student because no one cared about this. But this student was a good student, so he popularized this. So he said, okay, if you want to explain some mathematics to some physicists, you need to make pictures. Pictures are very important. Already in the 60s or 70s, 70s, maybe something like that. So Mandelbrot really did a revolution. But he said, let us plot this. How will we plot this, or how will we demonstrate this? Let us generate this on a computer in some way. And the way he did it in many different ways, but what we are going to do now is a random walk in 2 dimensions with fat-tailed distribution. They can be Levy, but for this discussion, it's not so important. So I'm going to assume that I can generate some positive R with something that can go like a fat tail. For example, mu equal 1, doesn't matter. Here R is positive. Now I'm going to generate a random walk. the random walk is like this. Okay, I'll do it in two ways. I'll also have, this is f1 and this is f2. F of r, this is exponential. So here the moment exists. This distribution looks something like this. The first moment, the second moment, everything is finite. This guy has a distribution, maybe looks like something like that. Now I'm going to generate, I'll start with 2. That's an ordinary random walk in 2 dimension. I start from a point, and I generate on a computer a random variable from this distribution. And then I generate a second random variable, an angle which is uniformly distributed on all these angles. So I choose, let's say, pi over 2, and then, or something. And then I plot this r. And then again, I choose a random direction uniformly with pi between 0 and 2 pi. And then I plot another one. And I do it many times. This is something you'll do on your computer, and there are many ways to do this. You'll get something like this. And this is very typical, this is like Brownian motion in 2 dimensions. You cross yourself very back. And what I wanted to plot here, you see these sizes are more or less the same. Because if you have an exponential distribution, the average, let's say here, is 1. But the probability of getting e to the minus 50 is 0. You will never find a big fluctuation here. Now, Mandelbrot said, OK, let us plot it, but now use this fat tail distribution that my teacher Levi taught me. And then I'll plot this thing. And then what he found, let's say for mu equal 1, but any mu less than 2, you see something like this. And then if you take here you have many steps. Let's say you have to think about it. I have 10,000 steps, whatever. Here also I have 10,000 steps. The number of steps here and here is the same in my computer that I run in my mind. And then if you look, you zoom up here, and you look inside, you'll see again something similar. Similar, I'm not defining what do I mean exactly by similar, because I defined it already mathematically before. So when you zoom in here, you see something similar.
This is a fractal.
This is a fractal. Now you can sell books and you are famous. But today they are called Levi processes. Levi was the mathematician, and Mandelbrot was able to show this to physicists, and then people said, oh, okay, we know things like this in physics, and now we can apply it to many things. It was psychologically, I think, very important that he plotted this and talked to this. Of course, at the beginning, everyone told him, no, this is bullshit. There's no such thing as a divergent variance. It's impossible. Actually, the history is much more complicated, because actually what Levi found was found in physics in a different way. I'll show you later, but for a special case. Anyway, why is this like this? First of all, again, you need to practice on your computer and generate these figures, and you'll see it for yourself. But what is the meaning that we don't have the mean? So you see what happens here. I generate a random variable. Its size is something. The typical size here, maybe at the beginning, is 1. OK, so you have one step. It's 1. But in order for the mean or the variance to diverge, as time goes by, as you make more and more steps, you have to encounter bigger and bigger steps. Because if all the steps are the same size, the mean and the variance will be something finite. What does it mean, infinite variance? Or is that the sum of the random variables squared is going to explode. If it's going to explode, the summand, when you sum many of them, one of them or two of them or three of them are going to be big. And in order for not to converge, you have, let's say, 10,000 steps, then you do 20,000 steps, then you need to find something bigger and bigger and bigger. So as time goes by, you have these bigger and bigger flights, with no characteristic scale. And this is something called today, this is called the Levy flight. What does it describe in nature? We will see in the next lessons, we will see that there are many examples of this that came. So Levy and the Russian school of thought was roughly 1920, 1930. The examples, or there was a few examples already then in physics, but the mathematicians didn't know about them. But then in the 60s and 70s and 80s, everyone was looking, oh, this is exciting. Let's look at these fractals. Let's measure, explain this. OK, maybe for you, 70s and 80s is already a long time ago. So we will discuss these objects in physics the next lesson, and see you then next week. OK?